Hi, today I'd like to go over the postulates of quantum mechanics as they apply to quantum computing. Um, just a little bit about myself to start off the presentation. My name is Leonard Woody. I go by my last name Woody. Author of the book Essential Mathematics of Quantum Computing. Also have a couple of roles here at Microsoft in quantum. I've got a QR code there for my book if you're interested. And I have a number of different degrees in physics, computer science, and software engineering. So a lot of this presentation is around what's affectionately called Mike and Ike within the quantum computing industry. It's the book Quantum Computation and Quantum Information by Michael Nielsen and Isaac Chung. It really is, to me, and I think others, the Bible of quantum computing. And a lot of the text that I have in this presentation is lifted right from there to make sure that it's kind of canonical in the way that it's presented. So very quickly, these are the postulates of quantum mechanics, and I'm not going to go through each one right here. I will go through them as we go through the presentation. But they are around the state space, first of all with the wave function, observables and operators, which are not as important within quantum computing because they are continuous, usually things like position and momentum. Quantum superposition, which is important, we'll go through. Measurement, which we probably all know and love, that collapses the wave function when it's done. Time evolution, which really allows us to do the actual computation. Entanglement, which is where the power of a lot of quantum algorithms come from. And then the exclusion principle in quantum mechanics is very important because it basically gives rise to the periodic table, but it won't be as important in quantum computing. So on the left here are the postulates of quantum mechanics that I just went through, and on the right are the postulates that are given in Mike and Ike for quantum computing. Most of the mappings from the postulates of quantum mechanics on the left are pretty easy to see. State space goes with state space. The number 5 time evolution goes with number 2 evolution. Measurement are the same. Composite systems is different, and that's really going to involve both entanglement and superposition when we get into that postulate for composite systems. So let's take a look at the state space postulate first. In quantum mechanics, the way that it's stated is that every state of a physical system is represented by a vector. And these vectors can be kind of, if you will, the normal vectors, say an n element column matrix or column vector, but they can also be functions. And the set of all the state vectors describing a given physical system form a complex vector space for the system, explicitly what's usually called a Hilbert space. And only those states which can be normalized to one or unity can be represented by physically realizable states. So those are kind of the conditions on the vectors within the Hilbert space. I've put an example of a state within quantum mechanics. This is the ground state for a simple harmonic oscillator. Just to give you a taste of what a lot of the functions are, or state vectors, if you will, are within quantum mechanics. Obviously, we don't have a lot if we keep with the circuit model, continuous functions and stuff like that, but I wanted to give you a taste of what those look like. In quantum computing, it's quite different. The fundamental unit of quantum information, as we all know, is the qubit. And we don't have to deal with continuous functions in the circuit model. We're just represented by a state vector, and it's just a 2-dimensional Hilbert space, so it makes things much easier mathematically. So the canonical example is, you're given a ket psi, you're then given a constant alpha, which could be a complex number, the state 0, and then beta and 1. Which is the state 1 and 0. So this is showing a qubit in a superposition with alpha and beta as its coefficients, and these are normal types of states that we would see in quantum computing. So let's move on to something a little bit more difficult and interesting, the evolution postulate. In quantum mechanics, we talk about the time evolution of the state of a closed quantum system, and it's described by the good old Schrödinger equation. So H is an operator. It's the Hamiltonian operator, as can be seen here within the equation here, and it's a Hermitian operator, so it's equal to its adjoint. And from there, you also have good complex number I, imaginary number I, Planck's constant, which we all know and love, and then the partial derivative with respect to t of the wave function itself. So unless you've done a lot of calculus and partial differential equations, this is not going to make a lot of sense to you, but it's really the way that physicists look at quantum mechanics. Again, for people in quantum computation, it's much easier. We kind of look at it from a unitary evolution, which is mathematically equivalent to the way that it's described within the last page on quantum mechanics. And the evolution of a closed quantum system, again, this is lifted from Mike and Ike, is described by a unitary transformation. So the state psi of the system at time t1 is related to the state psi prime at time t2 by a unitary operator u, which depends only on the times t1 and t2. So that unitary operator for us is going to be gates, things like the x gate, y gate, z gate, and these are unitary operators and allow us to evolve the quantum state as we compute with it. Ultimately, we could take all those gates, multiply them together, and come up with just one unitary gate to do that. The measurement postulate is a little bit different in the way that it's put within quantum computation within Mike and Ike. It's a more generalized form than is usually given in quantum mechanics. So I'm actually going to show that one first here. Quantum measurements are described by a collection of measurement operators. And these act on the space of the system being measured. And the index M refers to the measurement outcomes that may occur in the experiment. So if the state of the system is in ket psi immediately before the measurement, then the probability that you get M occurs is given by the probability measure given right here, which is a bracket with the adjoint of the measurement operator and then the measure operator itself. And then this is the state that you get after it. Additionally, Mike and Ike goes into the completeness, not completeness, relation here, where basically it says that all of the different measurements have to add up to 1, because we know that probabilities have to add up to 1. So what's usually used in quantum mechanics, at least in undergrad quantum mechanics that I've taken, is what are called projective measurements. So the act of measuring a quantum system causes the wave function to collapse to one of its eigenstates, and the probability of the system collapsing to a particular eigenstate is given by the square of the amplitude of the wave function. And we actually use this one within quantum computation as well. But the previous postulate is a more generalized form of this projective measurement postulate and allows us to distinguish quantum states when that becomes important in quantum computation. So this is how it's usually stated. I believe this is from Mike and Ike as well, that the possible results of a measurement of a dynamical variable A are the eigenvalues A sub n of the operator A corresponding to that variable. And if you use spectral decomposition, you can write the operator A in terms of its eigenvalues and corresponding projection operators, which are represented with ket bras this way. And if you sum all those up in a spectral decomposition, you're going to get back the operator. The probability is given this way. You can also use the trace, which comes up when we look at density operators. I plan to go through density operators in my next video. And the post-measurement, when we collapse the wave function, is given by this formula here. So these are projective measurements, and maybe more used to if you've done quantum mechanics undergrad, or if you've just done a little bit of quantum computation, this would be the way that it's usually given. There's one other that I didn't include in here called POVM measurements, which are also used in quantum computation and are gone over within Mike and Ike. I may do a separate presentation on those. They are used within quantum computation, but I decided to just leave them out of this particular presentation. And then finally, we're going to go through composite systems. If we only had one qubit, that would not be that interesting. We often have multiple qubits. So within quantum computing, the composite system is basically a tensor product of all the qubits or quantum states that we have, and qubit represents a quantum state. So it's if the systems are numbered 1 through n, and the system number I is prepared in the state psi sub I, then the joint state of the total system is the tensor product of all of those systems together. So since we have qubits and they are in a two-state space, of course this is where we have 2 to the power of 2, which is 4, 2 to the power of 3, which is 8. So as many qubits you have, your state space grows by a power of 2, and that's where you kind of get this, exponential growth from qubits is directly from this postulate. Other postulates that I alluded to earlier when I was going through the quantum mechanics postulates, I'll give in the next slide. Physicists aren't in total consensus on the postulates of quantum mechanics. In fact, there's papers out there where people try to put quantum mechanics through just 3 postulates or 4 postulates. So there's definitely an argument, I guess you might say, within the foundation of quantum mechanics on what the postulates are and how many there are. But I thought I'd go ahead and bring up some of the other ones that you may come across. I talked a little bit about the one around observables and operators. So when quantum mechanics and when you do your physics, you're interested in things like the position of a particle, what its momentum is, how much energy it has. And since those are very interesting to you in physics, you represent those by operators. A lot of times they're partial derivatives to do that, to derive that value that you're looking for. So they get you information about the system, but this information is usually a continuous variable. The Pauli exclusion principle is applicable to things like fermions, and the best example of a fermion is electrons, and two identical fermions can occupy the same quantum state simultaneously. So that, of course, gives rise to the periodic table because you can only have a certain number of electrons in each orbital of an atom, and so the electrons get farther and farther apart. Very important for physics, but not as important for quantum computation. The Born rule, we kind of subsumed that into our measurement postulate, but it can also be referred to as the Born rule, where the coefficients of the state vector give the statistical probability of attaining that particular state at measurement. And then some people have the state collapse after measurement as a different postulate. And finally, I just wanted to make sure I get my citations in for the great book by Michael Nielsen and Chuang. And if you're interested in the derivation of some of these postulates, there's a paper here that goes into that, which is kind of a good way to look at how current academics look at it. So thank you very much for your time, and I hope to see you again soon. Thanks.